so only the mic will pick up the audio.
Definitely time. Just got here for my class. Good afternoon, everyone. Good afternoon. Good afternoon, and welcome to the APS Colloquium. And we're privileged today to have one of our own faculty members, Dr. Dave Brain. It's a pleasure for me to introduce Dave Brain. He was an undergraduate at Rice University. He got a PhD here in the Department of Astrophysical, Planetary, and Atmospheric Sciences in 2002. He went to the University of California, Berkeley, was a researcher there until 2011. And he's been here since as an assistant and an associate professor. He's well known for his work, both starting as a graduate student and beyond, studying Mars. He's a Mars expert. He's a leader on space missions, including MAVEN and the Emirates Mars mission. And today, he's going to talk to us about retention of habitable atmospheres in planetary systems. Dave Brain.
Typical professor move. There we go. Mic on. No, not mic on. What's next for MAVEN? What can we learn about Mars climate in the big picture? Do magnetic fields matter and star-planet interactions? Not in the narrow definition that phrase now has 7 years later, but in a broader definition. Since you've already heard a lot about MAVEN in this previous talk that you remember very well, I won't do so much of that today, but it will come out through the talk because we use, my group uses a lot of MAVEN information to inform the other topics. Similarly, I won't talk much about Martian climate today, except possibly near the end. I'll instead focus on, do magnetic fields matter and what are the implications for how planets interact with their host stars? So the question that you may have heard me utter several times in the past several years is this 6-word question. 1, 2, 3, 4, 5. Yep, 6-word question. This is the question that gets me out of bed in the morning scientifically these days. Do habitable worlds require magnetic fields? It's a science with a capital S. And as I approached and passed tenure, I became increasingly interested in doing something that I thought was really fundamental, really big picture, and this is the big picture question that excites me now. On one hand, we have information at our disposal in the solar system. Earth has a magnetic field, a big global magnetic field, and it has life. Mars and Venus do not have global magnetic fields, and they do not have life. Therefore, the question has already been answered. It's very clear. Magnetic fields are required for life. Unfortunately, we run up against the statistics of small numbers, and so the question merits, in my opinion, further investigation. So you might be surprised to learn, however, that when I first began thinking about this question, the thoughts that would run through my brain, the images that would run through my brain are not images like the one you see on the screen. Instead, it's something more like this, pigeons. And that's because I heard this urban legend in graduate school when we talked about space weather and solar storms, that homing pigeons during homing pigeon races tend to get lost if there's a solar storm happening during the race. And this is a homing pigeon release during a race in the UK. And it turns out this urban legend is totally true. I actually have 5 or 6 slides about pigeons I could show you. I'm only going to show you one more after this one, but you can find websites on the internet about homing pigeon races that have solar storm alerts on the pages. Homing pigeons indeed get lost during solar storm events, and the thought is that the disturbance in Earth's magnetic field messes with their navigation. So the first time that this was really recognized was in the 1970s, and this is just my arrogant excuse to have a slide titled Italian Zoology of the 1970s in an astronomy colloquium. And you can see, well, you probably can't see, near the bottom someplace, and I can't find it anymore. Let's just go to the plot. They talk about homing pigeons getting lost. And here are 18 races for a total of about 1,200 animals between 1932 and 1957 in Italy, between Calabria and Parma. These 2 open circles here were during thunderstorm type events that occurred after the pigeons were released, and so you want to ignore those points. And there are 2 things that I'd like to show you about this plot. Number 1, wolf number is basically sunspot number, an indication of solar activity. As solar activity increases, the success rate, percentage arrival of homing pigeons, goes down because Earth's magnetic field has been disturbed, and the pigeons use Earth's magnetic field to navigate in some way. The second thing I'd like you to notice is that the maximum of this plot is 25% arrival, which if I'm a homing pigeon, I'm not going to sign up to be a professional homing pigeon racer. That doesn't sound good. And if I own the homing pigeons, that also sounds bad. You wonder in all these Italian homing pigeon races where the other 75% are going, and I just don't know. All right. Maybe they turn around and go to Iceland. I don't know. Yeah. Okay. So it turns out plenty of biological systems on Earth use Earth's magnetic field in some way. Sea turtles, it's thought, plenty of birds. There's this hilarious debate between 2 different scientific groups about whether cows sleep oriented with the magnetic field, and it involves Google images of cow fields and violent arguments back and forth. But this link between life and magnetic fields is not really influencing habitability of the planet. So let's get more serious and more related to my own research. So now when I think of magnetic fields and habitability, I think of this logical chain with 4 blocks and 3 arrows, and you could read this by replacing each of those black arrows with the word requires. So the logic goes, life requires liquid water requires an atmosphere requires a global magnetic field. And there are caveats with each of these arrows. So for the first arrow, we're inherently assuming Earth-like life in order, all Earth-like life requires liquid water. For the second arrow, liquid water requiring an atmosphere, we are inherently assuming that we're thinking about planetary surfaces, not moons like Europa of Jupiter. And more recently, with the discussion about Venus and life in the clouds of Venus, surface life or above. And then finally, for that last arrow, we are inherently assuming that global magnetic fields shield atmospheres, provide some protection for atmospheres. But there's a question mark there. So confirming or disproving this last arrow has implications for Earth and Earth's history, the history of habitability on Earth. It has implications for the planets in our solar system and also implications for exoplanetary topics. And here I'll pause for a second and say that for the rest of this talk, I'm neglecting the influence of a magnetic field on the surface radiation environment of a planet, but I'm happy to talk to you about why I think that's not so important, and influence on atmospheric chemistry. And I've had students working on both of these topics. Okay, let's explore a couple of those links in a little more detail with 1 or 2 slides. The first, from liquid water to atmosphere, we can think about the phase diagram of water. And in our daily experience, we think of the phase of water as being dictated by temperature. But as scientists, we know that pressure also plays a role. It's just our daily experience is in a very narrow range of pressures. So if we could put Earth conditions and Mars conditions and Venus conditions on this phase diagram, it would look something like this, where Earth's average temperatures straddle the solid-liquid boundary for liquid water in a very narrow range of pressures. Mars does get warm enough for water to be liquid, but at very low pressures, near the triple point, so that it's difficult for water to be stable as a liquid on the surface. Yet when we look at Mars today, there are dried up lake beds, dried up river beds that require long periods of time where liquid water is stable. This is one of the big pieces of evidence we use to say that Mars used to have a thicker atmosphere, something higher in this diagram than what it is today. And then poor Venus is just way off here in no person's land. And that's one reason that we talk about life in the cloud tops of Venus at lower pressures and at lower temperatures as well as being something to think about. Okay, another link is between atmosphere and global magnetic field and the shielding component. Here, as a community, we tend to think about atmospheric escape. Giving individual atmospheric particles enough energy to escape the gravitational well of the planet. And as atmospheric escape proceeds from planets, it's happening on Earth today as we speak, and every planet in the solar system, that should reduce the atmospheric pressure on a planet. And this diagram was made for MAVEN, and this is just a pause, a brief timeout, to talk a little bit about where that diagram originated. It originated with a blue ballpoint pen diagram, horrible diagram. And then the NASA artists, the Goddard Visualization Studio, turned it into this incredibly beautiful thing that is used all the time. And in my classes, I use this to highlight to undergraduate students the fact that a diverse array of skills are needed to successfully do and communicate your science. This was my best effort right here. Like, that's not even Pictionary good enough, okay? And this is what it got turned into. Okay, atmospheric escape. That's a term. You know what that means. You know what those words mean individually and together. But in our community, atmospheric escape is a term that refers to a suite of physical processes. There are many different ways to pull particles out of an atmosphere. I was going to draw each one, but a past undergrad made this super interesting diagram for me, and instead I'll tell you about some of those processes in words. So neutral particles can escape an atmosphere thermally, like hydrogen in this diagram. In any thermal distribution of particles, there are going to be some with a lot of energy. Those some with a lot of energy might have enough energy to escape the planet. If a whole lot of them have enough energy to escape the planet, then it's not just thermal escape or Jeans escape. Instead, it's this fluidized escape called hydrodynamic escape. Another way to remove particles is through chemistry driven by sunlight, photochemistry. So the oxygen here, the pink or violet oxygen, is supposed to represent photochemical escape. Sunlight drives exothermic chemical reactions. The resulting products of those reactions have enough energy to escape the planet. Another one would be ion escape, charged particle escape, here in this sort of stream of particles, leaving both a magnetized and unmagnetized planet. Again, can be important for heavier species and hydrogen as well, things like oxygen. We used to think of ion escape as 3 or 4 or 5 individual separate processes. And you could still think about it that way, but the ions don't care. The ions just respond to electric fields, and there could be many electric fields acting on them at any given time. And then finally, sputtering, that's the yellow O2 here, and this is a big splash. Some particle comes and crashes into the atmosphere with a lot of energy, and it could splash out other particles in the process. For some of these types of interactions, the yield is 100 to 1. One particle with enough energy can splash out 100 other things. So the takeaway here is that different atmospheric species can be stripped away by different processes. Some of those processes should be influenced by magnetic fields, like ion escape. It's pretty obvious that's a direct influence. Others, an indirect influence. But some shouldn't be influenced by magnetic fields. And then different processes can be dominant at different times in a star's history. So that makes this question that gets me out of bed in the morning a little more complicated to answer, a little more interesting, a little more fun, because it's not super straightforward. Okay, so when I came to graduate school, this was the canonical wisdom. Magnetic fields should protect atmospheres from being stripped away. That physics is easy, and it's illustrated very nicely here. For a big global magnetic field, charged particles coming from the sun turn left or right, depending upon their charge, and can never access the atmosphere, driving escape. But for a planet like Mars or Venus, the solar wind more directly encounters the atmosphere, and therefore more directly can drive escape. We have evidence that this may be true. For example, isotope ratios in the atmospheres of Venus and Mars indicate that escape has been an important process for those two planets. And those isotope ratios are stronger at Venus and Mars than they are for Earth, the magnetized planet, suggesting escape has been less important for Earth, the magnetized planet. We also see for Earth, the magnetized planet, the escape rates ebb and flow as the solar wind ebbs and flows as well. It's linked to what the solar wind is doing. However, in the last 10 years, this idea has come out as well. Magnetic fields should not protect atmospheres. And again, the physics is fairly straightforward. We don't need the particles to encounter the atmosphere for escape to result. Those particles are changing momentum as they get diverted around the planet. That momentum has to go someplace, and that can be transported down magnetic field lines to the atmosphere, resulting in escape. The escape isn't global like it would be at Mars or Venus. It's confined to the polar regions, but it might be very robust. And an analogy to think about here are the sails on a ship. How much momentum or energy could Earth capture from the solar wind if it didn't have a magnetic field? How much can it capture from the solar wind when it does have a magnetic field? It's a lot more. Some people think that magnetized planets actually have stronger escape rates than they would if they had no magnetic field. It's hard to perform that experiment with Earth without being an evil superhero, however, and so we're left trying to figure it out in other ways. So how can we resolve this? In my research group, we tackle this question in 3 different ways, and as a community, we tackle it in 3 different ways. Approach 1, comparing Earth, Venus, and Mars. Yes, statistics of small numbers, but we have a lot of data from those 3 planets because we can send spacecraft to the 3 planets and make measurements, try to figure out why one is too hot, one is too cold, and one is just right atmospherically. However, this is not a straightforward thing to do for a number of reasons. First of all, Venus, Earth, and Mars experience different conditions. On short time scales, that's obviously true. The sun is at the center of this diagram. Earth is in green. Mars is over here, and Venus is here. And on short time scales, they can experience very different driving conditions that can result in escape. If you happen to be making measurements at all 3 objects at the same time, there's no reason to believe that those measurements are directly comparable because there are different drivers. Even on long time scales, they experience different conditions because they're at different distances from the sun. So here are histograms of the velocity of in the solar wind encountered at Venus, Earth, and Mars, and the density. And the solar wind velocity is roughly the same throughout the inner solar system, but the density falls off as 1 over r squared. I should know that, and I don't. We'll move on. Just pretend you didn't hear that. The density is different. And so that for Mars, a high density day is pretty much a normal density day for Venus. And so these measurements that we've accumulated over long periods of time by different spacecraft from different agencies, analyzed by different people, it's not really an apples to apples comparison. So in our group, we've been trying to work on this a bit. So graduate student Josie Johnson has been looking at the configuration of the magnetosphere at Mars and at Venus using 2 different spacecraft. And statistically, she can make pictures of how the solar wind magnetic field drapes around Mars and how it drapes around Venus and what the average strength is. The Venus data are fairly ratty. This is probably not real. It's that those magnetometers are really close to the spacecraft that they sit on and therefore are disturbed by spacecraft magnetic fields. So ignore some of the chop in the Venus. Those look pretty similar when we look at the magnetosphere configuration for those 2 planets. But when she tries to isolate for different things, like the extreme ultraviolet flux, when she only takes times for which both planets had similar EUV fluxes. So for Mars, this would be high EUV flux, for Venus, low. Now the pictures start to look fairly different from each other. The magnetic field is strong as it drapes around Mars, and that barrier region for Venus is weaker and more confined relative to the size of the planet. In her submitted paper, she also goes on for 2 other external drivers off to the right, but you get the idea here. That Venus and Mars are actually pretty different from each other when you isolate for this same set of conditions. And we think the main reason for this is the fact that Venus and Mars are different sizes. Venus is double the size of Mars, but we don't have it fully mapped out how this is working, but at least some of it has to do with size of the planet. Okay, what about escape from these 2 planets? From these 3 planets, Robin Ramstad in our group has taken measurements of escape and from the 3 planets, organized them by the pressure in the solar wind. And oxygen escape from Mars is kind of no dependence or even an inverse dependence. Venus is weakly positive and Earth is strongly positive. Notice that Venus and Earth don't experience really low dynamic pressures. They're closer to the sun. But in regions of overlap, these dependencies are different. And as a matter of fact, the magnetized planet responds more strongly to changes in the solar wind than the unmagnetized planets do, which is very interesting. What's even more interesting is that this study was put together based on 4 previously published studies. He basically took the results of those studies and put them all on the plot. An undergrad in our group has discovered that there are more than 120 published studies on atmospheric escape rates from objects in our solar system. So there's a lot more to do to build out this plot and understand the different response of the planets to the solar wind. Okay, approach number 2, which is my bread and butter. I think most of the community thinks of me as a Mars person, and that's to use Mars. And there are 2 reasons that this is a good idea. Number 1, Mars has no global magnetic field, but it does have crustal magnetic fields that are very strong. So regions of the crust that are strongly magnetized, probably around 20 times more strongly magnetized than analogous regions in Earth's crust. And those strongly magnetized regions poke out above the atmosphere, and if they provide shielding, then they shield some parts of the atmosphere, but there are other parts of the atmosphere left unshielded. Now you have a built-in control experiment on one planet. You don't have to worry about differences in planetary size, distance from the sun, atmospheric composition, rotation rate, things like that. It's all on the same object. The other reason to be interested in Mars is that our observations of atmospheric escape from Mars, which come from MAVEN, are the best observations for any planet in the solar system. Our understanding of atmospheric escape at Mars exceeds by a lot our understanding of atmospheric escape at Earth or at Venus. We have the most comprehensive data there. So a couple things to tell you about. First, this is a shock and awe slide, and I said that I wasn't going to dwell on MAVEN too much in this talk. So I'll just give 1 sentence each on MAVEN-related results from our group. Yashui Dong in our group has looked at how escape rates vary with EUV flux from the sun. Nisha Schnepp has a paper looking at how escape rates vary with a lot of things, including pointing flux and solar wind pressure at Mars. Judith Bergfalk is looking at multi-spacecraft measurements, a NASA spacecraft and an ESA spacecraft, and using the configurations of those 2 spacecraft to learn about the system. This is a plot from when the 2 spacecraft were separated very closely. They were very close together, and so the electron measurements should look about the same. Rebecca Jolitz defended her thesis in our group, looking mostly doing modeling, but her 3rd analysis chapter, she used data to look at how much energy was coming from sunlight, extreme ultraviolet sunlight, how much energy was coming from solar wind protons and electrons, how much energy was coming from solar energetic protons and solar energetic electrons, to see how much energy was represented as input to the system that could be driving escape. There was this idea that solar storms are a huge energy input, but it turns out at Mars, that's not really true. Even during the extreme solar storm times, you're still orders of magnitude less energy than just the light coming from the star. Robin Ramstad has been looking at current systems in the magnetosphere using observations. And then I've looked at the crustal fields. This horrible looking map is basically telling you when the crustal magnetic fields at Mars are closed and when they're open to the solar wind, and if one region is more likely to be closed when the solar wind points that way versus that way. As the magnetic field in the solar wind switches direction, these crustal fields kind of open up and wave around and then close up again. Okay, so we're doing a lot in our group to understand both the Mars system and how atmospheric escape works from Mars. One that I want to highlight as particularly relevant comes from Tristan Weber's PhD thesis looking at escape, among other things, escape of ions in magnetized versus unmagnetized regions. We don't have to look at all 4 panels. Let's just pick 1 or 2. Let's do bottom left here. This is the strength of the magnetic field at 150 kilometers altitude. So magnetized regions, unmagnetized regions. And as a function of altitude, the color tells you the flux of O+ ions. And on magnetized regions, there are greater fluxes of oxygen ions than unmagnetized regions. And how those fluxes evolve with altitude is different in the magnetized versus unmagnetized regions. This suggests that magnetic fields do make a difference, and that in this case, the magnetic fields are enhancing escape for Mars. Okay, that's enough. How are we doing? I'm trying to add. I'm only like 3 or 4 minutes behind. Good. All right. Approach number 3 from the group. Use worlds in a box. Apply big simulations. Don't worry about this messy data thing from other planets. You get to play God and turn knobs and control things yourself in your own simulation. So here's an MHD simulation of how plasma interacts with Earth's magnetosphere. But this is illustrative here. I think I only have maybe 2 slides in this section. Graduate student Hillary Egan in our group used one of these global plasma models, held everything constant in her model for one of her thesis chapters, and just changed the strength of the planetary magnetic field. And these are weak, very, very weak planetary magnetic fields, 10 nanoteslas at the surface of the planet, where blue are draped magnetic field lines that connect at neither end to the planet, and orange are closed, connecting at both ends to the planet. And as the magnetic field strength increased, you get more and more closed magnetic field lines. In her simulation, she also looked at the escape rate of oxygen from the system, O+ and O2+. So I've hidden the result because I want you to anticipate the result. What do you think you're about to see? Do you think you'll see a flat line as a function of planetary field strength, meaning the magnetic field has no effect on escape? Do you think you'll see one that's high on the left and low at the right, so that low magnetic field strength, there's a lot of escape, high magnetic field, not much? Do you think it'll be low on the left and high on the right? At low magnetic field strength, there's very little escape, and at high magnetic field strength, there's a lot. Commit to your answer. Everyone forgot their clicker, so I will just show you. How many of you predicted that? Good. A couple did. We were very surprised by this and pleasantly surprised. It's a really cool result. And this result has since been reproduced by other groups around the world. For example, Tomoaki's advisor, Kaneko Seki, from his group has a similar result. There are similar results from Europe. And if we go back in the literature, well before Hillary Egan did this, there's a result for Earth that's not escape rate. It's instead Joule heating that has this same peak at intermediate magnetic field strengths. We're still working to understand exactly why this is, but we think it has something to do with the pressure in the solar wind and the pressure provided by the magnetic field. When those 2 pressures are in balance with each other, escape rates are maximized. But a reminder is that we're still at very weak magnetic field strengths here. Earth's magnetic field strength is way over here. And what we don't understand is if this curve will turn around and go the other way, what other physics becomes dominant as you go to larger and larger magnetic field strengths. Yeah? Venus and Mars are here, 0. Yeah. Okay, one more on this section. So I'm not trained as a modeler. I'm trained as someone who works with data, but I've worked a lot with modelers through my career, and we've now gotten to the point where we run models in my group as well. And so here are some examples of models where different people have isolated everything in the model and just turned a single knob. And I didn't realize till I put this slide together how many people have done honors theses with me with this general idea, but now I know. And so people have looked at angles in the magnetic field in the solar wind. Both Jay and Maddie did this. And that's supposed to be red and blue, very faint magnetic field in the tail. Shinran just did one this semester looking at the tilt of the dipole field of the planet with respect to the solar wind. And then Parker is actually using two different models. He's made himself expert in both an MHD and a hybrid model. He's exploring Earth's geomagnetic reversal periods and what happens during those times, and also trying to develop scaling laws for how escape varies as you turn each of these knobs. Okay, through all of this work, in our group and in the community at large, we've come to a conclusion, which is we can't really answer this question that gets me out of bed in the morning without also addressing a larger question. And that is you have to see that. What kind of planet keeps its atmosphere? Not just what is its magnetic field, but what kind of a planet in general? Does it have to be big or small? Does it have to be close to the star, far from the star? Can it be spinning fast or slow? Is there a certain type of atmospheric composition? We can't isolate the magnetic field question without answering these other ones as well. And that's because ion escape isn't the only type of escape. If ion escape goes down for a planet, does the neutral escape increase to compensate? We have to think about all of these things together. So suddenly the science with a capital S became science with a giant, very scary S that is really daunting. So for the rest of the time, I'll talk a little bit about this larger question, which was actually the title of the talk. Don't worry, everything before now wasn't intro. It was stuff I wanted to tell you. So there's a newly funded effort through NASA ICAR. ICAR is Interdisciplinary Consortia for Astrobiology Research. So it's supposed to be interdisciplinary. And it's a 5-year effort that was just funded this past summer. And the group that I'm involved with will model atmospheric escape from planets via all escape processes for about 200 different star-planet combinations over this 5-year period. So the title of the effort is Retention of Habitable Atmospheres in Planetary Systems. But before we submitted that proposal, we had a couple years together as a group, and we formed a team science center. And the name of that science center is MACH, which stands for Magnetic Fields, Atmospheres, and the Connection to Habitability. So you can see this question that is the root of the science center was really driven by the magnetic fields matter. It's just starting, so I'm going to tell you about what we plan to do and what our initial effort has been. So the main science question is, how do the properties of a planet and its host star combine together to influence the planet's ability to retain an atmosphere? And there are 3 or 4 aspects of this proposed work that I'm really excited about and think will lead us to answers. One is the team. So the team here I've colored, hopefully yellow, cyan, and green. Color blindness doesn't exist in this room, but it probably does. So there you go. Should have used symbols. But plenty of people in this group, like Kaneko Seki, think about Earth, think about planets, and think about exoplanets. But I've assigned them colors based on my perception of how the community perceives them. So we have people who come from the terrestrial community, and we have people who come from the planetary community, and we have people who come from the extrasolar planet community as well. Within each of those 3 categories, we have modelers and we have observers, people who work with data. So it's these 6 groups working together that I think can get us to appropriate answers. There are 4 objectives in this center. The first one, but combined together, the objectives lead to end-to-end modeling of atmospheric escape for a planet. So the first objective is the drivers for escape. We need to compute those inputs for an ensemble of star-planet scenarios. So not just our sun, but stars from every spectral class, and then of different stellar activity. So we have folks who are deriving the extreme ultraviolet photon fluxes for stars outside of our solar system. And we have other folks who are modeling the stellar wind and interplanetary magnetic field for those stars. And those inputs are then provided to the rest of the team. Those inputs then get passed to the modeling cohort of the team. Oops, I forgot to change the title. Objective 2 is model stuff, I'm pretty sure, or something about like that. But the 4 subtasks are to link these models together, which is trickier than you think, because we're trying to do it in a way that future modelers and people outside our team can also plug into what we're doing. So we're trying to come up with standardized formats for the outputs and inputs of these models, or at least data readers and data writers to translate from a standardized format to what those models actually use. We have to improve some existing models. And then here are one or two of the really important things, in my opinion. We need to validate the models. So focusing on our sun is a substantial part of what we're doing, because we have actual detailed observations that we can use to make sure the models are getting the correct answer. When we start moving to other stars, the validation becomes much more difficult. There are very few observations that can be used to validate. So I'm really proud that we're going to undergo verification. For every model, we have a partner model from a competitor. So 2 competitors have agreed to join our team and both run their competing models for the same thing and compare. If they get about the same answer, great. If they get very different answers, great. Now we understand where we need to do more work, and we need to understand things a bit better. Okay, objective 3 is then construct a model library and make it available to the whole community. So these are the 8 different axes that we are going to explore, and we have about this many cases along each axis. If you multiply those very small numbers together, you get a number that's greater than 400,000 model runs that we promised to do. But then we realized that and said, no, we're not going to do 400,000 model runs. We're going to do around 200 in 5 years, and we're going to strategically pick combinations that help us explore the parameter space appropriately. And some of these axes are not orthogonal to each other. And so making a pick along one axis automatically removes options along other. Then we're going to make a web-based interface where the community can come and enter the planetary magnetic field strength, or the solar wind pressure, or the EUV flux. It will access our library of model results and spit back an escape rate, probably for different species. Then there'll be multiple paragraphs in Latin, evidently, and maybe some plots of relevant models and links so that you can download the models. And then the community will be allowed to contribute their own model results as well, and we will host them and include them in what we do. Then finally, we're going to use our results to understand the connection between atmospheric escape and habitability and observations of planets around other stars. So 3 things we'll do are take our escape rates and estimate planetary atmospheric lifetimes. There are 2 ways I can think of to do this. One is just take the escape rate and multiply by the lifetime of the planet. But we know that planets and stars evolve with time, so we may more strategically pick multiple stellar activity levels during a stellar lifetime and multiple planetary states, and kind of try to integrate back in time. We're going to derive scaling laws for escape. How does escape vary as planetary magnetic field strength changes, as planetary size changes? And then Zach Berta-Thompson and Alini Vedato are going to construct exoplanet light curves in our modeled planets, so we can see how those light curves look when there's robust atmospheric escape versus not atmospheric escape as well, and tie back to observations. So we've started working on this by picking a test case. I said 200 model runs in 5 years. We're not going to do 40 per year. We're going to do 2 or 3 in our first year and really understand how to make this work. And then we're going to accelerate over a 5-year period. So the first thing that we've started working on is Mars as an exoplanet. We just took Mars today and we plopped it down around Barnard's star, a relatively quiet M-dwarf star, and have started practicing our end-to-end work. And I could talk for a long time about this, but I will not. But we have in red the measured spectrum from the star. Notice at visible wavelengths, an M-dwarf is much fainter than our sun. But at extreme ultraviolet wavelengths that are important for escape, it's comparable to or an order of magnitude greater than the extreme ultraviolet coming from our star. As a matter of fact, the extreme ultraviolet is a factor of sort of 3 to 5 times greater than it is for our sun from Barnard's star, even though it's a quiet M-dwarf. We then plug that into a model for a planetary upper atmosphere, the thermosphere and ionosphere. And here we can just compute the temperature as a function of altitude. For Mars today, it's the blue curve. And the model stops when you get to the exobase, the place where the atmosphere stops being collisional. And this model reproduces what we observe on Mars today to 0th order. Then we can just take the solar spectrum and multiply by a factor of 5 to approximate Barnard's star, and you get the green curve. The atmosphere is much hotter and much puffier. But when you then take the detailed spectrum of Barnard's star, even though it's still about 5 times the activity level, the whole atmosphere explodes in the model. It puffs way up to 1,000 kilometers and gets really, 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 really hot in the model. So we have another model that's working on checking this, and that is a model for hydrodynamic escape that also has to reproduce the upper atmosphere. This is run by Alex Glosser at Goddard Space Flight Center. And so we answer the question, does the atmosphere just flow away hydrodynamically? And it turns out that Mars around Barnard's star is right on the hairy edge of that happening. He can turn on the physics in his model, switch by switch by switch. And in one, the atmosphere blows away. In the next one, slightly more sophisticated, no, it doesn't. Next one, yes, it does. Next one, no, it doesn't. So it's right on the edge. All of this then feeds in to models for escape processes. And I've only shown one here in an effort to highlight the fact that we have multiple models for each thing. So this is the magnetospheric escape, the ion escape. And both of these models show that the escape of ions from Mars around Barnard's star increases by around 2 orders of magnitude compared to the escape of ions from Mars around our own star. These models have substantial differences with each other to the point where the modelers are really uneasy with me showing you these plots right now. They want to be talking to each other more and converging on an answer that they agree upon. I'm really excited that they're different. I think that's great. But we're going to have to socialize this with each other over the next several years. There are other escape processes as well, the neutral escape, the photochemical escape, the sputtering. I could talk about each of those. In general, atmospheric escape from Mars around Barnard's star increases with the exception of photochemical escape. The photochemical escape, that channel for escape gets shut off. And the reason for that is that for photochemical escape to occur, you need molecules near the exobase. And those molecules have to accept sunlight and break apart, resulting in escape. This atmosphere is so hot and so puffy that there are no molecules near the exobase. So photochemical escape goes away. This is just one out of around 200 that we're hoping to run, and we're learning a ton already. So it's really exciting. It's also really exciting learning to speak each other's language. My term, thermal escape, for exoplanet people, that's called photoevaporation. And understanding the differences between those terms and what really they mean has been kind of energizing for me to continue learning. Okay, I'm not done all the way. I'm going to try and take maybe 4 more minutes after this, but here's a summary that will come. I'll read the summary now. In reverse order, there's a ton to do, and we're working on which star-planet combinations lead to atmospheres being kept on planets. This was all started by excitement about the role of planetary magnetic fields, and they may not be shields against atmospheric escape. This is not my idea, by the way. Someone else had this idea first, Bob Strangeway at UCLA. I've been jumping up and down, shouting this idea to the community because I keep seeing popular news stories about Mars lost its magnetic field and then its atmosphere escaped, or this exoplanet is going to lose its atmosphere because it has no magnetic field. And I think it's too early to make statements like that. Those statements may be accurate, but we don't know. We haven't tested it all the way. So my role has been to sort of amplify this message. And then planetary surface habitability requires atmospheres that don't escape entirely. You need pressure. Okay, this is a colloquium talk. There's also a promotion talk. So I'm just going to take 4 more minutes on the promotion talk side of things. You probably don't remember this talk. This was my job talk. This slide was from my job talk in 2009-ish. Here, at the end of the talk, I tried to do some big picture. Where will this lead? So I just have 3 slides here. I didn't talk about much about Mars and its climate, but this is something that we're still thinking about in my group. Here's present-day atmospheric escape at Mars that MAVEN can measure. Here's what we think was happening early in solar system history when the solar corona was brighter in EUV, the solar wind was stronger. So trying to take these measurements and extrapolate back over time is something that's difficult to do, but you can make attempts. So before MAVEN ever arrived, a postdoc that I worked with tried to do it based on model results. Now we're doing it based on MAVEN data. And with an asterisk, my present guess is that ion escape from Mars is much smaller than we previously thought based on MAVEN measurements. Maybe only 5 millibars of atmosphere have been lost. And Mars' atmosphere today is 6 to 7 millibars. It's not anywhere close to the 1 bar Earth atmosphere or half a bar. So ion escape might be much smaller than we thought. The asterisk is there because I did this calculation in September, and I still need to double check that calculation. I could be missing an order of magnitude someplace or just wrong. My career has always involved, and I hope will always involve, spacecraft missions. So I've been working with MAVEN, you heard some about today. I didn't talk about EMM at all. There are missions in development that are slated for launch. And then there are missions that are in the pre-proposal stage as well, and now branching out to Earth, which is super exciting, and thinking about atmospheric escape at Earth. And there are 1 or 2 here that I haven't included and can't really talk about at the moment. Finally, I don't know who this is a lesson for, but I felt like making this point. Early in my career, I felt a strong urge to stay in my lane, to do things that are in my wheelhouse. But as I've gotten older, I've gotten more curmudgeonly or less careful or more interesting to just tackle something that I find interesting. And so I'm doing that increasingly. You know, Michaela's looking at asteroid and comet impacts onto atmospheres, trying to figure out if atmospheres grow or shrink as a result through modeling. Anna's sending charged particles into exoplanet atmospheres to find out how much energy and ionization and heating happen. Mike Rothman is looking at clouds above the limb of Mars using EMM. Because clouds on the disk of Mars, it's really hard to figure out their height. But if they're above the limb, you can figure out how high above the surface they are. I've been thinking about detectability of an ocean inside Triton using magnetometer measurements. And then I've become increasingly interested in thinking about the radiation budget of Mars over the past 2 years, when I realized that this diagram of the radiation budget for Mars is not based on data. It's based on a GCM, a global circulation model. We need the observations to validate every single one of these arrows, and I think LASP is the laboratory to do this mission. LASP is expert in doing half of these arrows for Earth, and so we need a mission out of LASP to do this for Mars as well. Okay, that was all I wanted to say. The very last thing I'll just leave up. I'm here because of many mentors, some of whom have passed on, some of whom are in the audience, and I'm super thankful. So I've tried over my career to give back as best I can, and it turns out in the process it's been way more rewarding than I thought, because I've learned more from them than they've taught me, than I have taught them. So I will put the summary slide back up in a minute, but I just want to leave this up for a minute. Okay, thanks.
So thanks a lot, Dave. And can you hear me here? Yes, great. And now this talk is open for questions. We're going to start with students first. Is there a good question you want to ask or comment you want to make? Please.
My question was one of the things you didn't talk about, which was why surface radiation wasn't important in your models. Because when I thought of magnetic fields for habitability, that was the first thing I thought of. I'm also not a planet person, so I'd love to hear something about that.
So it could be very important. Surface radiation could be very important. But a starting point that I have is Earth's current surface radiation environment. And half of the damaging radiation dose that you and I receive here on Earth's surface is coming from human activity. The other half is coming from the natural environment. Of the natural environment surface radiation, only 10% is coming from space. And that 10% could be influenced by magnetic fields. It depends upon the energy of those particles. So for Earth's surface radiation environment, something less than 5% is the kind of thing that could be influenced by the presence or absence of Earth's magnetic field. Now we go to another planet with a thinner atmosphere and no magnetic field, that less than 5% could grow and become important at that point. But when thinking about Venus and Earth, you know, I'm prepared to push surface radiation off to a later question. Maybe Mars, it becomes more important at that point. We have those measurements coming from the surface of Mars now. And when you go to exoplanet situations and really active stars and you know, a less strong heliopause or heliospheric magnetic field to deflect GCRs, then maybe it becomes really important. Yeah.
So my group has been thinking a lot about preparing for Habitable Worlds Observatory, and the list of targets selected for that that's been announced is like over 60% multiple star systems. So are your simulations going to look at the effects of planets potentially being in a multiple star system?
Yeah, so this is a wonderful question. There are a variety of people involved in selecting what kinds of systems we're going to model. And some of those people include Kevin France and Zach Berta-Thompson here at CU, people like Rachel Austin, who's a CU alum at Space Telescope, and Ravi Kaparapu, people who are engaged and involved in Habitable Worlds Observatory discussions. So they have said that we will at least pick some systems that are coming from the same list that HWO picks. The multiple star systems, I'm less sure about. I think it would be great, but I'm not certain right now which of our models could easily accommodate inputs coming from different directions and which could not. Yeah.
Okay.
Yeah. Great talk. I do have a comment, and that is, you've pointed out that extreme ultraviolet radiation plays a very important role in mass loss from exoplanets. But I want to say that extreme ultraviolet radiation is not a number. It's a spectral energy distribution. And that's important because of the efficiency of an EUV photon in terms of driving mass loss depends upon whether the energy goes primarily into photoionization, followed by recombination and therefore loss of a photon, or whether it goes into heating the atmosphere. And that depends critically on the spectral energy distribution.
Yes, wonderful
which is
point.
a very important topic.
Thank you for amplifying that. And I'd like to go back here and say that that is almost certainly what's happening here between the green curve and the red curve. The total energy represented in those two simulation runs for a thermosphere is the same. The difference is In the green one, we just took the solar spectrum and multiplied by 5 to have the same total energy as Barnard's star. In the red one, we actually used the spectrum from Barnard's star, and the atmosphere responded very differently, as you said. Yeah.
So, Dave, there are other planets in our solar system with magnetic fields, namely Jupiter, Saturn, and they have...
My thesis advisor is looking at me right now. Okay.
They have stronger magnetic fields and different solar wind conditions. Do you learn anything in studying those systems about atmospheric escape that might apply then to, habitable exoplanets, or just learning about it in the inner part of the solar system?
Yes, absolutely. I think that you can. The giant planets have a significant gravity well, so that escape there is fairly challenging, but I still think we can understand how processes operate by pulling them into the conversation. So a couple people on our team have done outflow models from Jupiter and are hoping to incorporate that kind of thinking. And then we have a person on our team who has some experience with Mercury as well at the other end of the spectrum. It's not fully clear to me yet what lessons we're going to pull, but we try to at least have some experience with big planets and really small planets beyond Venus, Earth, and Mars sized things. Yeah.
I just have a question about the geomagnetic reversals.
Yeah.
So we've had about 185 geomagnetic reversals on Earth in the last 80 million years. And they happen about every 10,000 to up to 1 million years. It varies a lot. But the field strength, magnetic field strength declines by 90% during reversals or failed reversals. So what is the impact on atmospheric escape or on the radiation for the biosphere?
Wonderful question. I don't know, but Parker's going to find out. And the several cool things. One, Earth's field is dipolar. During a geomagnetic reversal, Earth doesn't do this. That's not correct. Instead, it reorganizes and shrinks. The power goes into higher order terms, like quadrupole and octupole terms, and that pulls the magnetic field in. Then it flips, then it goes back out. And so it's possible that Earth's atmosphere is left exposed for hundreds of years while the reversal is happening. Homing pigeons are screwed during that time, and Parker will have to tell us the rest in about a year when he defends his thesis.
So there's time for one more question over here.
So what causes the crustal magnetic fields on Mars?
Aha! Good question. What causes the crustal fields? So we believe that most of those fields are remnant from when Mars used to have a magnetic field like Earth. And that global magnetic field is generated in the liquid outer core of a planet. And you require a temperature gradient with altitude to get that convection vigorous and moving. And Mars is a small baked potato compared to Earth's baked potato, so Mars cooled off quicker, and so it lost the ability to sustain a dynamo magnetic field. There's about a half billion year debate on when the Mars dynamo turned off, but by 3.3 billion years ago, it was definitely shut off. And so what was left were the regions of the crust that were magnetized in the presence of that dynamo. Should have been most of the crust of the planet. But any place that's been heated up since then through volcanism like Tharsis, or big impacts like the Hellas Basin, or whatever the heck happened in the northern hemisphere, has removed magnetization. And so we just have magnetization left from the most ancient parts of the planet. Yeah.
So thanks to all for your participation. That ends today's colloquium. Thank you all.